All right, guys, Mr. Antonucci here, and we're going to be talking about Section 7.2 separable first order differential equations, uninhibited and inhibited growth and decay models. We're going to have a couple videos here on this section. So the first thing we're going to talk about in this video is solving a separable first order differential equation. Now, first order differential equation has the form where the derivative is a function of x and y. And if it's separable, what that means is it can be written in the form m of x over n of y. In other words, m is a function of x alone and n is a function of y alone. And the reason they call it separable is because you can actually separate the y function in the dy and then separate the x function in the dx. So, um, oops. So for example here, if we have let's say dy dx equals x secant y. This is separable because we can, if we treat dy and dx, the differentials, as manipulative symbols, manipulatable symbols, if you will, we can rewrite this as dy over secant y equals x dx. We essentially just multiply both sides by dx and divide by the secant y so that we can get our x's and dx's on one side and our y's and dy's on the other side. Now, if I had an equation similar like this, dy dx equals e to the x sine of xy, this would not be separable because you can't separate it into just x's and just y's. Okay, because you have that sign of x times y. All right, now whenever we solve a differential equation that's separable like this, the first thing we do, like we did right here, is separate the variables. And then all we do is slap an integral symbol on either side and take the antiderivatives to obtain the general solution. All right, so we're going to actually run through an example of that right now. We want to find the general solution to this separable differential equation, as well as the particular solution. Okay, so I'd just like to copy it back down here. So dy dx equals 3xy squared. I can separate this by having dy over y squared equals 3x dx. All right. Now I can slap an integral symbol on each one of those. And I could write this as y to the negative 2 dy equals 3 times the integral of x dx, just rewriting it a little bit. Then the antiderivative of y to the negative 2. Notice you're integrating with respect to y here and with respect to x. So on the left side, we're treating the variable as a function of y. So it would be y to the negative 1 times negative 1 equals, this side would end up being x squared over 2 multiplies the 3. Now, you might be thinking, okay, why didn't you write the plus c on the left side? Well, essentially, if you did, okay, you would have plus c here, call that c1, and then plus c2 here. And we could rewrite this as negative 1 over y equals 3x, 3 halves x squared plus C2 minus whatever C1 was. But this right here is just going to be a constant anyway. So we would write our final answer here as negative 1 over y equals 3 halves x squared plus c. Okay, so this is the general solution, and it can be written in many equivalent forms. And the domain of this general solution is restricted to all points x and y, where y is not equal to 0. And the reason y can't be equal to 0 is because y is in the denominator here. Now, sometimes they might ask you to solve it as a function of y, and then we would have to solve this equation for y. Okay, so if we look at part B, we want the particular solution when y is 2 and x is 1. So we're just going to substitute that in. I'll actually do that right over here. Okay, so we would have negative 1 over 2 equals 3 halves times 1 squared plus c. All right, so negative 1 half equals 3 halves plus c. And if I subtract the 3 halves to the other side, it would give me negative 4 halves, which is the same as negative 2. So c equals negative 2. And then I can write my particular solution. Negative 1 over y equals 3x squared over 2 minus 2, where y is not equal to 0. Let me just specify that restriction right there. Okay, well, that's it for this one, guys. Hope that was helpful to you, and the next video we'll go over the second objective here.